So starting with the maximum ratio combining technique. If you look at the diagram here on the right, the diagram shows you that you have different branches, and those branches are going through a combiner. Those branches are different in terms of additive noise and different from in terms of the channel experience. We're having different receiver for each case. In maximum ratio combining, each MAD filter output, each receiver output, is multiplied by the conjugate of the channel, and that's alpha k represent the amplitude and theta k. I'm using colors here to follow up. So alpha k in blue represent the magnitude scaling, and theta is going to be the amount of phase. So this is assuming that, of course, we know theta and alpha. We can estimate them correctly. So an optimal combining assumes correct channel estimation. The effect of this multiplication, for the green, for the phase, you multiply by the conjugate. It means every branch is going to be adjusted accordingly, and for the weight, the signal will be scaled by a factor that's proportional to the signal strength. So strong signal will have more weight, weak signals will have less weight. The effect of this multiplication is to have an output energy per bit, which is the sum of the energy per bit over all or each channel. So if we have a certain energy here, and certain energy here, and certain energy there, and by this co-phasing adjustment, we'll have the total energy per bit will be the sum of all. And that would maximize the signal to noise ratio for the system of L different branches. Now I'm repeating the model with Andrea Goldsmith notation. So we have, instead of L branches, we have capital M branches. And you can see here that we have M antennas. The received signal S, the transmit signal is S, and the received signal Y in red is nothing but a delayed, a scaled version, and then we add the noise N. We have used Z before, so it's a complex Gaussian noise with a given mean and variance. So it's just some few variables change, otherwise it's the same concept. So our job here is if we use this combiner, this is called a linear combiner. And the reason we call it linear combiner is that the resultant signal is a linear operation, scaling and adding of the input signals. This is a linear operation. You can think of a nonlinear combiner where you can square, cube, whatever, any linear operations could be done, but we are focusing on linear combinations. That said, we have the following the following tasks to do. What is the instantaneous signal to noise ratio per channel? And what is the average what is the average signal to noise ratio per channel? I mean, on the average, so we have one signal to noise ratio here, another one, a third. What's the average of all of that? How would you process the received signal Y in a way to form a maximum likelihood estimate of S? How do we combine them in a way to maximize the likelihood of recovering the original signal or information S? What is the instantaneous signal to noise ratio at the output? And what is the average signal to noise ratio after processing? Remember, we're making a distinction between instantaneous and average, because with the fading effect, we will have instantaneous, which could be very different than the average. The process of co-phasing or branch coherent detection is shown here, that once we receive the signal, we expect that we need somehow to estimate the variables, the scaling factors, and from the received signal, and phi, the delay, and then of course we adjust or we weight accordingly. Without being able to estimate, then we cannot do the coherent co-phasing and the coherent detection or combining. Here is another figure just to illustrate the concept of combining. Here is that input signal, channel, different noises, and then at the receiver side we are scaling, and then we're combining together. Now remember that there is signal to noise ratio on the ith branch, which is shown here in green, the green dot, and then we have the signal to noise ratio after the weighting, and then we have the signal to noise ratio after the combining. These are the locations shown with green, yellow, and then red for illustration. Now let's get back to answering the basic questions, including the signal to noise ratio per branch, instantaneously or on the average. I'm marking this with red here so we can follow up gamma 1, gamma 2, up to gamma capital M, where capital M is the number of branches. As we mentioned before, we have different notations, and this is one of them. So we have gamma 1, gamma 2, and so on. So the instantaneous signal to noise ratio per branch can be said as the average. It's the expected value of S squared because S changes from one symbol to another. And because we're looking for energy, we're looking at the square. The scaling factor alpha or A here shown is to be squared for the energy divided by the noise, which is N naught. Now, average signal to noise ratio per channel, this is the instantaneous. It depends on the exact alpha or A for a given branch or multipath. Now, if you want the average, then you need to take the expectation even of A squared. So A goes inside the expectation, and we get the average value. That would give you gamma bar. Our job is to design a maximum likelihood detector that give you the estimate of S. And to do this, we assume that we are given beta. What is beta? Beta is the scaling factors, that's the channel state information. And this is not a very strange assumption. We assume that there is other circuitry that is going to take care of estimating alpha and theta for all the branches. Under this assumption, under correct estimate, and for every given S, I want to find what will be the received signal. And then I will take the one that maximizes the probability of Y. So I will try given S1, 2, 3, I will try all the symbols, and we'll take P, Y with the highest probability. So we are looking at maximizing the probability, and we're looking at not the maximum value of the probability, we're looking at the argument. The argument is that's going to maximize this. If you take a maximum of a certain quantity, you're going to also take the maximum of the log. You get the same answer. Why? Because the log is a monotonic function. So the maximum remains the same. It does not go up or down. We can show without going into details that maximizing this probability is equivalent, is proportional to maximizing the negative of the following quantity. That's maximizing the probability means minimizing the distance. And this is the distance between Y minus beta S. That's the scaled version of S, that the received signal. I want to get the minimum distance closest to the constellation point. If we open the bracket, we can show that without too much focus on the math, we get Y squared plus 2 times first times second, and then we got the following quantity. We have three terms, sorry. Now we're looking for, okay, the first term is not function of S. So this does not change from one S to another. We're going to change S. So this is not a very important quantity. This term is not function of Y. Okay, so it does not depend on the received Y. The only term that's function of S and Y is this quantity. And we can see that we have beta H times Y is a sufficient statistics. That's knowing this quantity is sufficient to make a maximum likelihood decision. What's beta S? What's beta H? Okay, this is the quantity that is Y is nothing but beta S plus N. And if we separate these two terms, the first term here, this multiplied by this give you the signal space, and this times this give you the noise. I mean the second term times beta H times N. So this is why in the numerator here you get the squared, okay, beta H times EB squared times S squared, divided by beta H times N squared. And then if we open the bracket, that becomes beta S. So this will give you the magnitude of beta, or the normal beta fourth, of times S squared. And then we need a little bit of linear algebra here. And then we can show at the end of the day that this will give you the summation of sum of A squared times S squared divided by N squared, which is nothing but this sum will give you the sum of the signal to noise ratio in every single branch. So the conclusion is if we use maximum ratio combining, and that's shown here because the received signal is defined to be beta multiplying beta H by Y. Okay, so Y here is defined to be beta S plus N. Then we can say here that the maximum for this will be the sum of the instantaneous signal noise ratio. To continue the maximum likelihood, we would like to weigh each branch with complex conjugate of the channel. That's better branches get larger weight. Co-phasing plus multiply with amplitude. The output signal to noise ratio would be the sum. The distribution of the sigma depends on the distribution of the original signal to noise ratio. If we are having Rayleigh, then sum of MID exponential random variables will give you chi squared, and that's given by the following quantity. So on the left hand here we have the we have the PDF. On the right hand we have the CDF. For the chi-square, the mean is known, the variance is known, okay, and we can divide the signal to noise ratio per branch by M. If you want to get the diversity gain, so that's then the mean would become gamma, and the variance becomes gamma squared. That's if we want not to increase the power. Let's divide the total power by the different branches. We can compute outage probability and average error probability based on this, and because we know what's the new distribution of the signal to noise ratio, diversity shows up as a slope in outage probability and the average probability. That would be improved slope if you divide by M. So M is array gain. We collect more power, and M here is we will get in the case of diversity gain, the channels look like a. In the following, we'll see the performance or the distribution, the output signal to noise ratio distribution, how the signal to noise ratio will look like after the maximum ratio combining. For example, we're going to pick the branch signal to noise ratio to equal to 1. So the signal to noise ratio per branch is assumed to have an average of 1. So in the following left diagram, you see that this is on the x-axis. We have got gamma, the signal to noise ratio, and here is the probability distribution. So if m equal to 1, we get the normal exponential decay curve. But we can see as we increase m, we are having a shift to the right. The signal to noise ratio distribution improves. So in the green curve shows the case of m equal to 2, and then for the red one it's m equal to 3, and then you can keep going. I'm showing the example of m equal to 10. Now if you look at the amount of advantage we get, for example, if you compare the m equal to 2 and m equal to 3, you can see that there is a array gain if you go to 10. So depending on the number of branches we have, we get array gain. So the average, if you have 2 branches, the average becomes 2. If you have 3 branches, the average becomes 3, and so on. Simply because with maximum ratio combining, the resultant signal to noise ratio will be the sum of the individual ones. On the right hand side here, we see the case of diversity gain. So in this case now, we'll assume that gamma equal to 1 over m, gamma equal to 1 over m. So every branch, the power or the energy will be divided across the branches to make the two cases, to make the case of one branch and multi-branch under more fair comparison. So we can see here that the average always remains 1, but the distribution is different here now. So for the case of m equal to 10 or m equal to 10, you see you have less cases where we have low probability. So the curve gets concentrated. We get shifted from the very low to the right. Of course, there is also another change here to balance things out. But here there is no array gain, and channel would look like more identified Gaussian noise as we increase the order of Gaussian. And as we increase the order of number of branches, we get more of. So we have seen the impact of the signal to noise ratio. Now, if we take the impact and substitute into the outage probability, the probability that gamma summation, that the gamma after the signal to noise ratio has been added, combined, and the probability that it's less than a given threshold, we will find out that we'll have a shift. Okay, we have a array gain, shift, and diversity gain. As we increase the number of branches, we go to the left. Okay, of course that's for a given target, and then of course we have also on the right hand side, we show that if we want to focus on the diversity gain, where we divide all the branches with by m. So there is going to be a shift by log 10 base term. That's going to be there's going to be a slope change. Okay, so there's going to be a slope change improvement in terms of signal to noise ratio. Okay, now that's when gamma equal to the threshold. That's the point where things will tilt around. Now, so in general, if you want to, we looked at the outage probability, and we looked at the probability of error. In general, if you want to find the performance as you need two things. We need to specify the modulation. So we're saying the probability of error is conditional probability on a fixed set of on the given gammas. So the average error is obtained by averaging probability of having a certain, if you want to call it P sub P or P sub S, over possible values of gamma, and that's given by the purple color. So what combining does changes the second factor. We need to find the PDF of gamma B, then carry out the integration. So we have found the gamma B for different cases, MRC and so on. So for example, under rarely fading, the MRC results in, without showing the derivation, you know that the output is going to be the sum of the individual branches, and also we can get also the probability of the distribution of gamma for a given number of branches given by the following equation, and then substitution will give us the probability of error. The movement due to diversity, the error rate decreases inversely with L power. So similar analysis could be carried out with to find different modulation techniques, coherent, non-coherent, and so on. So if we do all of this, we'll get the curve on the right, which shows the performance. Okay, so the first set here is for L equal to 1 for one branch. That's comparing FSK, DBSK, and PSK. We know that for fading channels, it's going to be a linear. And for L equal to 2, it's improving dramatically for L equal to 4. And as we increase L, it becomes like a waterfall curve. What are we paying for this advantage? Of course, we are paying complexity in the system, because you have to send multiple times. If you look at diversity gain, then you're looking at complexity, and if you look at the array gain, then you need, of course, to increase the power also. So the following curve shows the average error probability for the case of binary phase shift keying, and we can see here that on the left hand side you can see that we have the array gain. Earlier we have seen the outage probability. Now this is the probability of error, if you want to call it P sub P, or that's the probability of the error of the symbol error rate. Okay, so now on the right hand side